Hello everyone, welcome to Handmade, here on the show where we code a complete game live on stream. Yesterday we pretty much finished making our texture downloads synchronous so that the OpenGL driver would be happier about them. We had one bug. We kind of ended the stream. We didn't have time to go debug it. We finished typing it all in, but we didn't have time to debug it. On the light rail today, home from climbing, I think I may have thought of what the bug was, actually. Just popped into my head for some reason. So yeah, this might not take very long if I'm right. But if I'm wrong, then we gotta go debug it. So I don't know which is gonna be. Maybe this will be quick, maybe it'll be not so quick. Day 326. So if you want to follow along at home, day 325 source code is the source code to be reckoned with today. Here is Mr. Gamey Pants Poo. And if you remember where we were yesterday, we had this sort of call down at the bottom of Win32 Handmade, where we were doing our stuff. And what we did is we did a begin ticket mutex, and we grabbed out the whole list of texture operations that was waiting, and I do believe I'm correct. Even just looking at the code here, I think I'm totally right about what the bug was. And then we had our end ticket mutex. We then took a look to see if there had been any texture ops in there. If there were, we went ahead and put processed them and then put them on the free list so that they could be reused. And what we found was, and this is why I think my brain clued into what the bug was, assuming I'm right, and I think I am. What we found was a bunch of our textures loaded, but some of them did not load, right? And you can kind of see some of those are just blank white textures. So the question is, what happened there? And at the end of last stream, I had said something like, well, it looks like at some point we stop loading textures, but I don't think that's anything to do with the ticket mutex, because the ticket mutex looked pretty solid. Well, what I forgot was we have a last pointer as well. I decided to retire texture ops in series, if I remember correctly. And so that texture queue, let me just make sure I'm not crazy, but that texture queue, I believe, has a first and, yeah. So you can see here we've got a first and a last, and we're only resetting the first. So all of our future attempts to load textures were getting stuck after a link that was already on the free list, right? So it's just going to keep sticking things on the free list, which is not going to get them loaded. So I believe that is really the only bug that we had, potentially, if I'm right. Like I said, don't know if I am, but yeah, that's just the way it is. And the other thing that I'd point out is, when we get this first out here, we could get the last out, and then OpenGL managed textures would not have to return us the last because we already have the last. So really, maybe it's a slightly cleaner thing to do to say, oh, don't bother keeping this. You don't need to, because we already know what the last op was. So you're fine. Just let's go ahead and get it here. Right? So we get the first texture op, get the last texture op, and assuming there is a first texture op, we then go ahead and do all our stuff. We can also assert that there's a last one, because if there's a first one, there has to be a last one, right? And off we go. So hey, there you go. That was the bug. So that's good news. And now, in theory, our texture downloads are all synchronous. So we should not be having the problems on NVIDIA cards and stuff like that that we were having before, or occasionally with ATI. At least that's the theory. Now, I don't know how good these texture downloads are. So I was interested to see in this cutscene here. I'm interested to know if we can maybe get some profiling. I don't remember. I guess we didn't have. There it is. Oh dear. My goodness. Why are we so slow with frame profiling on? Does anyone know? That's crazy. Uh, huh. Look at that. If we're in threads mode, we go very, very fast. If we're in frames mode, we go extremely slowly. Let's pause right there and see what's going on. If I pause there and look at the clock's display, oh, it's our sprite graph sorting. Yeah. You know, we need to just turn sorting off for the debug display, I feel like. We just need to tell it to don't bother sorting because it's just a waste of everyone's time and energy with all these little guys here. You know what I mean? They don't need to be sorted for any particular reason. And that build sprite graph just ends up being very, very costly. But what I suppose I could do for the time being, because we know that our build sprite graph code is very debug code limited, I could do this as well. But maybe I should go in while we're at it, since we don't have to do the other debugging we were going to do today. Maybe I should go in and make it so that that stuff doesn't get sorted. It's crazy how much different that speed is there. But anyway, all right, so, you know, here's our frame layout, and you can kind of see what most of the time being spent is here. In fact, you can kind of see in here we're spending most of our time doing that there. Most of the time is that frame display. I just want to see what happens at the changeover point if it's a problem, frame time wise. And it does not appear to be. So it appears that the synchronous texture downloads... Oh. Nope. There it is right there. So we do have one bad frame, right? You can see it. OpenGL render commands, 72.6 milliseconds. How come we can't see that frame? Like, how come it doesn't... I feel like this display is bad. Like, this is... I need to fix this display at some point, because I want to be able to see those single frame hitches. And I can't see them right now. So that frame is not... It's not doing its job, right? Yes, you can kind of see... So I don't know. What the best thing to do there is. I'm thinking maybe, you know, that's a good argument for trying to do some stuff with the pixel buffer objects or something. I'm not sure. But you can see what I'm worried about there, right? We get this like frame hitch at the time when the textures have to download. This is why I would have preferred them to be downloading asynchronously because I was worried about what was going to happen there. I'm not sure what that's necessarily from, right? And so what I'd like to do is I'd like to get rid of that if I can, because everything else is nice and smooth, but that transition point is, you know, is not. And I think we're still giving the game plenty of time to understand that stuff. So, I mean, the driver plenty of time to understand it. So I feel like maybe it's worth trying to do the pixel buffer objects just to see if we can reduce that transfer time. Because, yeah, maybe, you know, having the additional copy is a really big problem for it, or who knows exactly what's going on there. So it might be nice if we could allocate those in, you know, in GPU space or something like that, so that we wouldn't have that problem. Yeah. know. I don't know whether we should do that now or whether we should wait till later for that. It's really hard to say. But yeah, so hopefully you can see why I don't love that. You know, it's difficult to see it happen, but it's definitely happening, right? Like it's not something we can really perceive because it happens at the flip, so you don't see the hiccup happen per se, but it looks like it's definitely there, at least according to our timings. So unless there's something else that's going on there, I'm assuming that that's a pretty clear indication of badness. I should probably just make a little indicator too that just tells us when we have a bad frame, so we know. Like maybe it just puts up a little thing that's like, hey, there was a bad frame 2 frames ago or something like that. You know, a frame that's like an outlier in terms of how long the frame took, something like this. So there's certainly stuff we could do there that would be nice. But anyway, that is what that is. And the bug is gone. So this was our asynchronous texture downloads being reliable. So I'm going to say asynchronous texture downloads are now synchronous, but we get hiccups, which makes me grumpy. So yeah, I don't know, like I said, when we want to address that, but I think we probably are going to want to address that at some point. I'm probably not going to be super happy with that. It might be fine for in-game downloads, right? Like when we're just hopping around here and because the textures are so small, you know, that I could see that being okay. You know, those download hits, you maybe can just be slipped into the frame without a problem. But I don't know, right? Those cutscene ones definitely can't, because they're just downloading a ton of textures. That it doesn't look like the card is doing those as promptly as they could do them, or maybe it just needs more lead time, I don't know. But since it's hitting on exactly that one frame, I think that suggests to me that the driver is like waiting till we actually do the GLText image 2D, and then it's doing it right then, right? Well, no, it has to wait till the GLText image 2D, obviously, but it's not necessarily overlapping it at that point or something, or just the copy to GPU viewable memory. Maybe that's all of it. And if that was the case, that's great, because that means that pixel buffer objects would fix it. But if not, then yeah, then not. Okay. So let's see here. Let me do what we were gonna do though, and sort of fix these here. I'm gonna take a look at our to-do list and put some things in here. Frame view not showing bad frames. Disable sorting. Yeah, I think that should do it. Entity system, what to do about geographic disparate entities. Might be parsed to get streams of a region. Blah blah blah. Real projections with solid constant project unproject. I think we kind of did a lot of these, but that's okay. So I think the only thing I wanted to put on here was pixel buffer objects for texture downloads. All right. Yeah. All right. So let's take a look at the clan compatibility situation. Voidstar to GLUint and vice versa has been fixed, according to this. So I guess this part here is not a problem. So it looks like we're mostly talking about like the printf and the function macros that are the problem here. And yeah, I don't know about the function macro one, but the snprintfs being not supported and being something that should be replaced, that is something that we could probably do pretty easily. I don't know how to get to this. Didn't look like it. Oh, maybe here. Let's see. That. Let's Let's see. Some printf functions. So it looks like it's using vsn printf on other functions. So, I guess we have a couple different things we could do here. But I think since I don't really want to use the C runtime library long term, I think probably what we would want to do is be able to just do our own printf or something. Just take a look at what we're doing printf-wise and maybe try to replace it with something else. So I'm going to take a look, and I'm just going to see everywhere in the code where do we use a printf or an sprintf or things like that. So in the debug stuff, what is it? nprintf. So it's snprintf-s. And so, yeah, it looks like basically that's, the Win32 code. I don't know why the Win32 code is using that. To be honest with you, I don't even know what this is. Handle debug cycle counters. That's not something that we even use anymore. Let's get rid of that entirely. Debug draw vertical. This is the sound debug. Okay, let's get rid of all this stuff. I don't really want any of this stuff in here anymore. Okay, because we would want to put that in our regular debug system now. Okay, so let's try that again. I'm going to search for snprintf-s, and now we've just got here test the play cursor, right cursor. Let's get rid of those. And there's another snprintf, again with that right cursor in there. What is this guy? Handmade internal. All right. So yeah. So now I think we're just left with stuff in the debug system, and I guess we just have a lot of snprintf-s's through here because we're just printing out various values. And so all of those are the same. Then we've got ones that are kind of just used throughout. And so I'm assuming we know what we use here. We have %s, %f, %d, %u, sfud. I think it's behind my head. All right, so SFUD and that's really it. So we would basically just need a printf that handles S, F, U, and D. Right? That's what we would need to do. So we could, if we wanted to, implement one of those and see how far we get, right? It probably would be fine. So strictly out of curiosity, if I eliminate these, what happens? And yeah, you can see you've got A2TOI and snprintf-s are basically the two things that actually get used there. So let's just assume that we get rid of those. And let's go ahead and try to replicate them. ATOI is a lot easier, obviously, than anything else is going to be. I don't know where that A2I actually is. Oh dear. Why does it say if pipe count equals 1 and there's nothing there? Is that what's supposed to be there? Debug parse name. If the pipe count is 1, it does nothing. If the pipe count is that correct? Did I accidentally delete what was there? No, that's the way it's been. Isn't that a little weird? I'm curious to know. I feel like, isn't this the sort of thing that the GitHub should be able to do for us? You know, I mean, can it look back at handmade-debug.cpp and tell me why we have a blank line there for no reason, apparently? Right here. Can it do anything like that? Am I asking too much? Am I way out of line here? Yeah. Not feeling great about it. Like, hey, this is the line. Can you tell me anything about the line, please? I guess not. Yeah. No. All right. So I'm not going to try and learn to use GitHub because I don't really want to learn to use GitHub. But point being, that's a little weird. But whatevs. Anyway, we've got some functions that we have to replace. Now, ATOI we actually already wrote, if I remember correctly, because inside our Handmade OpenGL, we had to check for the version number. And so we had this sort of situation here where when we wanted to do essentially ATOI, it's this thing right here. So what I could do is I could basically make an ATOI in here that's like a shared version of ATOI, right? That's like S32 from ASCII Z or whatever, right? Or maybe just from Z string, right? And so you pass in your little @ there, and it does exactly what it does, and then it returns the result. So OpenGL parse number, we can actually make that just be a generic function now. And then in this place where we were doing A2I, I can just do S32 from Z and get the line number back. So I think that one's fine. The SN printfs are going to be a little bit more involved. The reason for that is that while it probably won't be too hard to do a crappy numerical output thing for %d, %u, and obviously %s is trivial. %f is like rocket science, trying to print a floating point number. If I remember correctly, really recently there was like a new way of doing it that wasn't heinous, and maybe I'll try to dig up that paper so we can use it. But like doing a %f print is like insane, or was insane, and I'm hoping, I'm crossing my fingers that they simplify it now. But like printing a floating point number is an epic disaster. We'll get to that when we get to it, but just trust me for now. Real bad, real bad. So let's pretend we're gonna have one of these here. And we'll just have, a format string function or whatever. And we'll have like the sort of dest size, dest format string, and, proportional whatever, something like that. And then we can also have a separate version, format string list or something, which is the one we'll probably actually call. And I'll talk a little bit about how these guys work. I think this is like a Vararg list or something like this. I don't remember how these guys go. But anyway, so we'd want to call format string with dest size, dest format, and the ... In place of our sn printf. And so, yeah, like... This gets a little bit into the vagaries of the C and C++ default calling convention. And I'll go ahead and sort of give you a little bit of a light sort of introduction into how these guys work. Well, you know what? Let me actually do it this way because I think this might be a little bit more interesting to see. But I'll give you a little background on it, and then we'll get that part of it going. And then we'll see how far we can get in reading the format string. So where's my Win3? There it is. This is my like little dummy project that I made for searching for things. Yes, prepare the solution. Keep on preparing that solution. Good job. So if I want to do a VA start here, and I want to go to the definition of the... Okay. The package server has stopped working. Well, that seems bad. All right, so anyway, these guys, VA start, VA arg, VA end, which we'll be using, and you'll see those are defined to go to these sort of intro macros, which I believe get redefined yet again in here. But anyway, here's the actual macros themselves, and you can kind of see what they're doing. So this doesn't really have to be a mystery. I'll cut and paste these guys out so you can sort of see what's happening here. But hopefully it'll make a little more sense as I walk you through it, because it's actually it's not that mystical, and it's kind of interesting to see how this stuff ends up working. Anyway, that address of I'd like to get as well. Where are you? Go to definition. There you are. Let's grab that out. Copy. And actually, you know what? Since I hate C++, let's actually use the non-C++ way. There we go. So let's talk about this, what we have to do here before I dive into it. And let me give you a little bit of a background on what's going on here with variable argument list stuff. So as you know, here on day 326, 306, as you know, variable arg lists. Normally when we call a function, and we've talked about this a bunch of times, we'll see a function signature, and it looks something like int foo, int x, right? And then we've got some stuff in here, and this stuff uses x, right? And so we've talked about this before, where we sort of imagine, because the C specification doesn't really necessarily say very much about how the stack is supposed to be allocated or moved around or any of that sort of stuff necessarily, but we do know a few things. But what we know abstractly in terms of what's happening is just that there is such a thing as the program stack, which is a bunch of memory that is used, and as you enter functions, things get pushed onto the stack, and as you exit functions, they get pushed off. And I believe the stack grows negatively on x64, if I remember correctly. So, as you push stuff on, you're going down, lower down the stack, as opposed to up, right? In our memory arenas, we push onto them, so our addresses get higher. I believe the program goes down. Don't quote me on that. It's one of those things I never remember which way, because I don't program in assembly language. If you program in assembly language, you would remember since you'd be doing it all the time. Anyway, so what ends up happening when you call a function, right, is the parameter for the function, assuming that it fits in a register, will just stay in the register, right? So if it can pass the values to foo in a register, then it will. But you can imagine having stuff that's too big for registers, like maybe this passes a whole struct, like there's a struct bar or something that needs to get passed and it's got a ton of stuff in it. You know, you could imagine there being stuff that you can't fit. And of course, when you can't fit something, then it needs to be pushed onto the stack. And so what ends up happening is, you know, you push on, say this bar here that happened, that goes on there. And if there was another bar B, you know, that would go on there as well. And you just kind of go on there. When this function executes, it's going to use these locations where those things were pushed to do work on A and B and whatever. And then when it's done, it's going to pop the stack back to here, right? So you basically have this pattern execution is every time you call into something, the stack is growing. And then every time you return from something, the stack shrinks, right? And that's how, you know, those calls sort of work. So what happens in a variable argument list function is actually very simple. What happens is we have a function like int foo, int x, but then instead of specifying what comes after the int x, we just know that there's some more functions, right? I'm sorry, some more parameters. So what happens is at the call site to foo, these extra parameters just get pushed on to the stack, just like A, B, C, D, whatever, they just get pushed on, right? Then, when the function returns, they will get cleaned up, usually by the caller. Since the caller knows how many pushed on, it will actually do the fix-up to pop them off, at least in the old days. I don't really know how the x64 ABI works. I haven't looked at it in detail myself, so I'm not sure. But somebody who knows how many things got pushed on will make sure that it moves the stack pointer back to where it should be, right? And so when you actually do this, sitting on the stack is all this data that got pushed on based on how many parameters you specified, like with a printf. You know, you specify the format string, and then you put as many things on the end as you want. Well, each one of those gets pushed on the stack. But now the question is, how does the actual function get them off of the stack, right? Because we know that typically we just refer to things by name, and the compiler is silently, every time we talk about x or a or b in that function foo, it just knows where the offset is in the stack. But since there is no function signature here, we just know there's a bunch of random arguments that nobody knows what they are. We can't refer to them by name, and the compiler doesn't know where they are. It just knows there's some sequence of them stuffed on the stack. So that's where the macros for VA, start, VA end, etc. There are these macros that the C library provides, which basically involve taking the address of the parameters here, which I believe are then required, like in a Vararg's function, I believe the compiler is then required not to pass the final named argument in a register. I think it's required to pass it on the stack so that it knows where it is. I think. That's my recollection. But basically what these macros do is they use the address of the last named variable to know where the next named variable is going to be. And then you just say, exactly like we do with like our raw memory stuff, you just say what you think it should be, and it will advance by that much, right? So if I think there's going to be an integer there, it will advance by an integer. And it just hopes I'm right. And so that's where like the format string of printf comes in, for example. That format string of printf is just a string that printf parses, and when it sees something like %d, it knows to advance one integer's worth of space on the stack and pull that off as an integer, right? So all these Vararg things are doing is they're walking the stack like regular memory, just like we do, and they're using the format string to figure out how big and of what type the thing on the stack in that location is, right? So it's very, very similar to what we do with our push struct stuff, right? Only in this case, it's using a string and it's parsing the string. So we just need to do exactly that, and off we go. Now you can see here, right, exactly how these work. They work exactly like I just said. The Vararg start part of things, you can see it takes the address of whatever the function, whatever the variable is that you give it, and the variable you give it has to be the last one, right? So it has to be this one right here, because like I said, it's going to look after it. And then it adds however big that thing is, because it needs to skip over it. Now you'll notice it doesn't use size of, but it rather uses int size of. And what does int size of do? Well, int size of rounds the size of that thing up to the nearest integer boundary, right? This is plus, you can see it doing it here. It's rounding up, right, to the size of the nearest integer. The reason for that is because that's the spec of Varargs. The C spec says Varargs are passed in size chunks that are integer width, right? So even if you're only going to pass 1 byte, it still uses an int's worth of space on the stack for it. I don't know why it's spec'd that way. It just is, right? And to be honest, I think that's not compiler specific. I think that might actually just literally be in the C spec that it is int sized. I just think that's true. But don't quote me on that. Maybe it is compiler specific, but I think that's just actually the way it's specified. So that's it, right? And you can see how you, when you do CRT Vararg, right? So C start, it's like getting the address to the first one. Vararg is pulling off one argument, and you pass what the type is, and you can see it looks just like our push struct, right? We're going to cast to that type, and we're going to in here say advance by however big that type has to be, like take wherever the stack is, we're going to move it that far, we're going to advance, and we're going to return wherever we were before, because that's, you know, that's where the thing actually was. So this is just shorthand for like, hey, I need to advance this pointer forwards by the size of the thing I consumed, but hey, the user wants to get back where I was before, so I'm just going to subtract that out, you know, to give them the right return value. VAN doesn't really do anything. It's really just, I think, some kind of a tidy up thing in case it needed to reserve something for, I mean, maybe some compiler implementations need to do something that would have to free something here or something like that. I don't know. So you're supposed to call VA end, but it doesn't do anything. Not on MSVC anyway, and I don't think on LLVM either. But on some compiler somewhere it might. Or maybe on like a different platform. All right. So anyway, if we go ahead and do these guys, we don't actually need to keep these here. We can use like VA start, VA arg, and VA end. And I guess what I also want to point out is I'm doing this in 2 parts. And the reason for that is I would like to be able to call format string with a varargs function, or from somebody who themselves was a varargs function and already got the list, right? So really the VA start, VA end are going to be here, and they're going to sort of create the list, right? This is our arg list, like so. So these guys, I don't know why I just did that. There we go. These guys create the list, and then we'll just call the function. Return the result. And then this format string list right here is the guy who will do all the work. He has the arg list, so he's going to pull off the things in the arg list as he understands what they should do, right? Okay. So what we want to do now is we want to, you know, loop over these characters. And I'm going to consume different numbers of them, so, you know, honestly, I'll probably just do this. It'll be that way. So what we're going to do here is we're going to take a look at what the at value tells us, right? And in this case, I think I might not really need a switch yet, right? Probably what I want to do first is just say, you know, if at equals %, then I know that I have to do some sort of parsing, right? And if it doesn't, then I know I'm just retiring a regular character. So I want to just try to get this started in a very basic way. So what I'm going to do first is I'm going to try and just make something that just writes to the buffer, and it strips out just the percents, right? So it's not going to do any conversions yet. So what I want to do for this is I'm going to add the utility thing here that's like a format dest or something like that. And format dest is going to have a size and a dest pointer, something like that, so that I can say like format dest, and maybe something like this. And that's just so I can keep track of how much space I have and where I am in the destination, because that just makes it a lot easier for me, right? Then when I'm done, it's pretty easy to see how much space I actually used, because all I have to do is say, well, wherever I ended up minus wherever I started is how much I used, right? So that's pretty basic. Now, what I would like to do in all cases also is say, assuming that the destination, if dest.size, assuming that there is any destination at all, I want to make sure that if I run out of space, I always null terminate. So what I want to do is at the end of everything, I want to say, if there is size remaining, right, then I want dest, and then maybe I'll make that an at. If there's size remaining, then I want to null terminate. If there isn't any space remaining, then I want to, that's not what I wanted. If there isn't any space remaining, then I'm going to overwrite whatever the final character was with a 0, because I never want to not have a null terminator at the end. So yeah, if there is space remaining, we'll just null terminate. If there isn't space remaining, we overwrite the last character with a null. And we know that we can always overwrite the previous character because we know we always have at least some size to begin with. So there's no way we can ever have a fault there by going before the buffer. So when we come in here, I'm just going to go ahead and say, okay, I'm going to output a char here. So I'll just say like outchar dest, whatever the character actually is. And this will just be a really simple function. Again, we're not going for speed here, certainly. But all this does is say, okay, if dest size minus dest at plus equals value, right? So all I'm doing there is just putting characters into the output buffer. So that's really all I wanted to do at first, and I'd like to go ahead and get that stuff working before we try to do any of the Vararg stuff. And then inside here, while we're looping through at, actually, I guess I could write this a little more succinctly, like so. And in here, I'm just going to advance it without doing anything. So now we can get rid of all this stuff that was just there, for example, just to let you know what's going on. And so now we should need, what is it, varargs.h, I think? Yeah, there we go. Too many actual parameters for macro vararg. Okay. va start, I should say. Go to definition. Go to definition. But that's how many there's supposed to be. Is 2, right? Am I missing something? I must be missing something. Well, let's look here. Arg pointer, previous param. How many parameters did you think there should be? Oh, you know what I just realized? I included the wrong function. Varargs is the old one, standard args is the new one. That's probably why it's probably a different macro. All right, so now all we have to do, and by the way, when we finally get rid of the CRT as well, we're going to have to copy and paste essentially those Vararg macros ourselves because you have to have them, right? So that has to be per compiler eventually. But we'll only need those. We won't need the whole printf, right? Because we're implementing the printf ourselves. Anyway, so snprintf is now our format string call. And we can get rid of this weird dance we had to do where we had to pass the size twice, which I don't really understand why, right? But that's what it actually should look like now. Excuse me. Conversion from size t to u32. I'm going to go ahead and say we'll let format string, just to make it easier on ourselves, we'll let format string take a full size there. There's no real reason for us not to, so we could just let it take memory sized stuff, and that's fine. Let's see, from N64 to U32, wait, didn't finish that guy, there he is. So yeah, so now I just kind of have to go through here, and I'm going to switch to the other one so my head's not behind it. But I'm just going to loop through these guys and change them to format string. So there's format string, and sort of get rid of all this ugliness. It's like much nicer this way too, because now we don't have these weird snprintf nonsense things that it wanted us to do, which is nice. Go. You know what's interesting is we could also make this more systemic if we wanted to. The whole at plus thing, we could actually just make that be our own sort of string out thing, because we already have that dest one, right, that I made for the actual printf function itself. So we could actually, if we wanted to be Mr. Reusing Pants, we could actually just repurpose that for this as well. Like, you can kind of see what's happening here. We could totally do that. So maybe that's a cool idea as well, right? A lot of times you can just sort of see stuff like that. You know, you can just sort of see like, oh, okay. You know, I see what this function is doing. It's just concatenating a bunch of things together. And that's sort of what I needed to do inside the other function as well, to prevent me from writing off the end of the string potentially. And so maybe I just make a little thing, a little cursor-like thing that I can just use to stream out strings, and maybe that's really cool, you know? Who knows? Maybe it's not. I don't know. I really don't. Meow, meow, meow. Sorry, this is a bit boring. Not coming up over my own typing area. That's not polite, Mr. Notice. That's not polite at all. Again, nothing happening here really than me just like rearranging, getting rid of the cruft that was in there from using snprintf, which is kind of a stupid function. I don't even really know what the point of it is. I'm not sure what the impetus was for it taking two sizes. What else we got? Almost there. Yeah, and like sometimes it wanted two sizes and sometimes it wanted one size, depending on like the type of the thing we were passing or something even weirder than that. I remember it was just super strange. Okay. So I think now we actually have everything ready. The actual size of this guy, I guess we'll return a UMM in this case, is just going to be, you know, wherever we started versus wherever we ended up, right? So this is where the last write was. This is where we, excuse me, this is where we began. So that's really all we should have to return there. Does not have an overloaded operator. Right you are, sir. Let's see. Format string list. Dest size destinate. Format arg list. Initializing conversion. UMM to U32. Where is the conversion? Ah, there it is. Okay. So in theory, we now have jump back to Handmade. We now have our own printf happening, but well, first of all, we have a bug, obviously, but we've got no actual formatting happening, right? Now, what's the problem here? My at pointer is null. How did my at pointer become null? Let's find out. So here's the dest. Dest init is null. Dest size, ooh. What did I do? So I guess it's okay to pass null here or something? What happened there? Buffer at plus equals format string. How did that end up getting destroyed, I wonder? Well, let's find out. If I can. So we've got our at there. Oh, don't care about that. Looks like Casey's got a typo. So we start with the format string. We loop through the format string till we get to a 0. We null terminate. Which seems reasonable. And then the result that we return is wherever we ended up minus wherever we started. All right. Let's take a look at that in action. Bloop. And so what am I passing here? End minus at, loop in there. Dest size is 256, dest is there. So we got dest size 256, dest init is what you expect. We're just going to increment at forwards. We're going to do an output of that, whatever this value is. Assuming that there is size left, we're going to subtract it. And then we're going to write to wherever this guy was pointing, whatever that value is, right? And that seems reasonable. Ah, yeah, there's a nice typo for you. You can tell it's been a slow night. There we go. And so I think, hopefully that's all for our typos. I think we should now be printing things out just without any actual formatting, right? So all of our stuff is just essentially the format strings, and that's it. But off we go. So that's a reasonable scaffold for it. And basically what we have to do now is implement the actual formatting in here, which, like I said, is not too hard for everything except for F. %F is just real bad, if that makes sense. So I'll go ahead and go to the Q&A, and we'll see what everyone's Q's and A's are. Pseudonym 73, printing floating point numbers, a faster, always correct method. This does look like the paper I was thinking of. Yes, this in fact definitely does. Yeah. So, maybe we have to read through this. I have not implemented it myself. Maybe we have to read this and implement it, because we don't really have. If there's no easy way to print a float and have it be right. There's an easy way to print a float and really sloppily, but. Canucles, short recap of what we've done today. We just started replacing snprintf. And the reason for that is just so that we won't be relying on as much of the C runtime library. We're slowly kind of getting rid of the C runtime library, so we'll be able to compile on Linux easier as well. Sizik, blame in GitHub lets you see the change history. Okay. I don't remember seeing a blame button, but I'll look for one. Popcorn says, What does -1 in des.at -1 do? Well, remember, bracket syntax in C is just the same as pointer arithmetic, essentially. So all that means is it goes back one element of whatever dest.at is pointing at. So since dest.at is pointing at characters, it goes back one element. So it's pointing to the element before the one that at's actually pointing at. You can stick any number in here you want, 17, -50, whatever. And it will basically move by that number times the size of whatever the pointer is pointing to. And then that is the thing you will be addressing. I want to start getting into this series. Is there a way to easily compile, run this code on Mac OS X? So I don't maintain a Mac OS port because I've said many times we're not going to port till the end of the series. But because it's just a lot of work involved in maintaining a port if you're sort of showing how to bring the platform layers up and you're changing how things work and so on. So I don't want to do that till we've finished everything and are just doing a port, basically. But other people have. So if you've pre-ordered the game and you have access to the private GitHub, there's people who have put macOS like SDL ports and stuff up on there that you can look at. There's also some ones that aren't up to date, some older ones like Handmade Penguin that are up to date that are SDL ports. But yeah, so other people have made macOS X ports, but that's not something that I will be doing till much later on in the series. No more questions? All right, I am going to wrap it up then. All right, thanks everyone for joining me for another episode of Handmade Heroes. It's been a pleasure coding with you as always. If you would like to follow along with the series at home, you can always pre-order the game on handmadehero.org. It comes with source code, so you can play around with it. We also have a forum site you can go if you want to ask questions, a Patreon page if you want to support the video series, a schedule bot that tweets the schedule at you, and an episode guide featuring past episodes you can take a look at if you are trying to catch up with old parts of this series. That's about it for today, and this is the last episode of the week. I will be back here next week for the last few episodes before I am going to have to be gone on vacation for a little while. So until then, how long is the break? The break's going to be a while, at least a couple weeks until I'm back. So there'll be a bit of a break. But yeah, there'll be some streams next week. So that's I'll be back here before break. That's about it. Hope to see you guys next week for the last few streams before break. Until then, have fun programming. I'll see you guys on the internet. Take it easy, everyone.